Welcome to MTH232 class. This is our fourth class where we are going to discuss explicitly on what I titled Existence and Uniqueness of Solution of Differential Equations. You remember that we've had Module 1 Unit 1A, Module 1 Unit 1B and 1C where we've talked a lot on the concept of differential equation. So in this video now, we want to study another aspect of it, which is somehow theoretical, but I will try all my possible best to explain to you. But let's come to think of it. If I want to solve a particular problem, what do I need to know? Do I even need to know? It's very important for me to know if there exists a solution. I can't just be solving a problem knowing fully well that it has no solution. Why would I be doing that? So we don't like students to really waste their time on problem that has no solution. Even in real life situation, you will notice that it's very rare for us before we can see a problem that it has no solution. Of course, you can. I know you may all agree with me. To some reasonable extent, there is no problem without a solution. Seriously, even if at all you don't have any solution physically, then spiritually, by seeking God, you can get a solution to it. So, which means that most problem, real life problem, they do have solution, but to a reasonable extent, some of them may have more than one solution. That is where we need the concept of elementary differential equation. What about the case whereby the problem has more than one solution? What will you do? Even what if my own solution is the same thing with the solution of another person? What does that mean? It means that the solution is unique. So these are the things we are going to study in this class, and I believe that this will help you a lot to be able to think through about multifaceted problems with many conditions, and then that will help us to really come up with a unique solution. Definition of term. As you can see on the screen, we have a typical problem of first order, and in this case the y dx is equals to what? Fs, y. Now, if we consider the condition to this problem, because we can't solve this problem without the condition. For this one we need just only one condition, but since we are dealing with first order, we need just only one condition. If you are dealing with second order, you need two conditions, and if you are solving third order, you need three conditions. So in this case, we have on the screen first order ordinary differential equation. But before we can call this one IVP, we need to see the the conditions, which is x naught, y naught. Now looking at this now, this is what we call first order ordinary differential equation initial value problem, because we only have the condition specified at a point. At what point? At x naught. Now let's take for instance example 1. If you look at this example 1 now, you will see the y dx is equal to 2x plus 1. And what is the condition? The condition is what? When x is 2, y is 3. But look at this one, you notice that the function we have here is 2x plus 1. Before we can solve this one, this function fs, y, it plays a lot of role. In fact, it will even help us to know a lot of things about the solution. Because what? If you cross multiply, you will need to integrate 2x plus 1. And that is where the solution will come from. You can now see now that fs, y play a lot, is very important in order for us to solve the problem. Let's consider example 2. Now you can see now another problem again. If you look at this one, you see now that in this case, our fs, y now is now 2x plus y. So for us, the method we are going to use to solve the first one will be quite different from the method we are going to use to solve the second one. That is why in this class, we are going to consider so many methods of solving first order. In fact, I'm talking about only first order. There are many methods. There are many methods that we're going to use because the nature of x of fx, y is very important. If you look at example 1 now, you see that in this case, if you cross multiply, you only have dy is equals to 2x plus 1 dx. So to integrate that one is very simple. But if you come to the second one, you cannot integrate directly like that. There are many things you need to do. That is why in this course, I will expose you to so many methods. So please bear with me by the time we are solving, and I'm trying to call your attention to several methods. Why we may use a particular method and why we may not use the same method for another problem again. So bear in mind that this kind of problem is associated with the nature of the function fs. Now, let's assume that I ask you to describe the problem on the screen now. You will notice that this is actually first order differential equation of initial value problem. So for us to solve this thing, there are many things we need to bear in mind as far as the solution is concerned. In fact, it is very important to note that the solution we are going to obtain for this particular problem on the screen, the solution must be a function. That is it. The solution y of x that we are going to obtain in this case, it must be a function. In fact, remember that when you are solving simultaneous equation, what you have is what is a constant. When you are solving quadratic, what we have? You have a constant or some constants. Quadratic, you have two constants, right? And many problems like that. But most times, whenever you are trying to solve a differential equation, what you are going to have as the solution will be a function. Not only that, the function must be continuous. And we cannot say a function is continuous like that. That statement is not complete. We must say that the function must be continuous at every point in a specific domain. So which means that we need a particular rectangle in which the function is only continuous inside of it. Okay, take note of that. Number 3, the function we are talking about, it must be bounded in the domain. There are many things we know. If you remember in our WhatsApp discussion, I've shown you the function of 1 over x. And you know that 1 over x at x equals to 0, such a function is not continuous there. So which means that we can never have a solution like that. We may never have a solution in such a way that at some point in the domain, the solution is discontinuous. We are not going to have something like that. So the 3 important things now about the solution of ordinary differential equation is that the solution we are looking for, it must be a function. The solution we are looking for, it must be a continuous function at every point in a specific domain. Do you remember that in our WhatsApp group I've explained this issue of domain to you? Now, how do we get the domain? We are going to use this particular condition. In fact, it's the first thing that we need, because this condition x0, y0 will let us know a particular point in that domain. And at the same time, the function that we are looking for, it must be bounded in the domain. Now, you notice that the 3 points that we mentioned above now is strongly dependent on the function fx, y. Either the solution will be a function, it has to do with fx, y. Either the solution will be a continuous function, it has to do with function fx, y. Either the solution will be bounded, it's dependent on function fx, y. So please take note of that. So the function, it plays a lot of things in the solution of ordinary differential equation. Now let's talk about boundedness of functions. If you can see in the screen now, you notice that we have 2 functions there. One is blue, while the other one is red. One of them is bounded, while the other one is not bounded. Now, if you look at this very well now, you notice that this will be useful to help us to know boundedness of function. Number 1 now, the function presented by purple line is actually bounded, by plus m and bounded below by minus m. Now, in that case, m could be a real number or perhaps a complex number. So a function f of x that is defined on some set x, which could be real or complex value, is bounded if the set of its value is actually bounded. Now, what I'm talking about now is that if you look at this now, you will see 2 broken lines. Those 2 broken lines, you will see that the function that is represented with red is strictly between the 2 broken horizontal lines, the 2 horizontal lines. Why that of blue? It's not. So that's what we are trying to say now, that this red line is bounded below and it's also bounded above. Let me further explain this again now. Let's say we have a particular function f of x, and that f of x is less than or equals to a. And at all the values of x in a particular large set x, if that function f of x is still lower than a, or perhaps it's equals to a, what does it mean? It means that the function is actually bounded above by a. As you can see now, I have put a above now. If the function is indeed a real value and is actually greater than or is equals to b, what does it mean? It means that the function is bounded below by what? By b. Don't forget that here we are talking about the function, not the point b. So the function f of x is actually bounded below. Don't forget that f of x is greater than b. If f of x is greater than b, that means that the function is actually bounded and b is the below f of x. Now, a real value function that is now bounded above and it's also bounded below, we can call that one, we can say that such a function is what is bounded. Don't forget, the function cannot be only bounded below without bounded above. The function must be bounded above and below before we can say that that particular function is bounded. Now, let me now explain to you now. Let's say, for instance, we have f of x that is less than or equals to m. What does it mean? It means that the function f of x is bounded above by plus m and is bounded below by minus m. So, next thing we are going to consider now is called the continuity of a function at a point. Look at that statement. Continuity of a function at a point. Now, if you have a function f of x and it's continuous at some point, c, if it's continuous at the point c of its domain, then it means three things. Number one, it means that as s is increasing to c. Now, let me give an instance. Let's say c is 5. Now, as x is moving closer to 5, that would be as x is moving from 0 to 1 to 2 to 3 to 4 to 5. So as s is tending to that particular 5, the function 2 must be equals to what? F is when we put the function c inside of it, that would be f of 5. So in that case now, there are three things involved. Number one, the expression above, it implies the function f of x has to be defined at c. It is only when the function f of x is defined at c that we can have f of c. Number two, that f of c, it must exist. And then if it now exists, it now means that the limit as s tends to c f of x, it must be equals to f of c. So in that case, if you now look at this graph now, you see now that this is the graph of function 1 over x. Now at x equals to 0, what can we say about this? You will notice that f of 0 in this case, it's mathematical error or infinite. Yes, some calculator we said 1 over 0 is math error. But what it means is that 0 goes in 1 in uncountable times. That is what it means. So, and because of that, you will now notice that this has violated the second rule, because in that case, 1 over 0, it does not exist. So then we can now say that 1 over x is not continuous at s equals to 0. Or we can say 1 over 0 is discontinuous at s equals to 0. But don't forget that from minus infinity less than 0, the function is continuous. From a point greater than 0, let's say from 0.1 to infinity, the function is also what? Continuous. The function is only discontinuous at s equals to 0. Now let's take a look at this problem now, existence of solution of ODE IVP. Now let's say we have a particular function f of x, the particular function the y dx is equals to f of x, and x of x naught equals to y naught. Now let's take a look at this diagram now. I believe you will like this now. The first thing I need to do is to locate the point x naught, y naught in the domain. Look at this now. I already have the point x naught, y naught. Now, what is the next thing I need to do now is that the function fx, y, it must be continuous at all points. What do I mean by at all points? See, this is a very broad point, and I need to be specific. I can't just say f of x is continuous at all points in x, y. The next thing now is that I need to use the condition, which is x naught, y naught, to let me know the boundary. And immediately I know the boundary, I will have a perfect triangle, a rectangle. Then from that rectangle, I can indeed now come up with the domain where the function is continuous. Number one, let's say we have x minus x naught, absolute value is less than or equals to a. What does it mean? it implies that x0 is bounded below by x0 minus a and is bounded above by x0 plus a. That is not all. Let's say I also consider y minus y0 has a value less than or equal to b. What does it imply? It implies that my y0 is bounded below by y0 minus b and is bounded above by y0 plus b. So what is next thing now? Then I can now say that my function fx, y is bounded in the domain. In this case now, I put r, which is a real number here, is general, isn't it? But at the same time, I need to be specific that I'm talking about the rectangle domain. So then we cannot say that the ODE IVP above, it has at least one solution. And that solution is only defined within x minus x0 less than or equals to h. See, in this case, in this course, we are not going to talk about the theory. But if we are to go detail into the theory, there is a way that we can calculate A. There's a way we can calculate B. There's a way we can calculate H. That will give us a perfect solution. But that one is beyond the scope of this course. So before we proceed now, another thing that I just want to remind you, and I said, dear students of MTH232-NOUN, please don't forget that whenever you are dealing with any problem of differential equation, for instance, first order initial value problem, and you have the function fx, y, don't forget that the function can depend on x and y. It's okay. So don't forget that the absolute value of x minus x0 less than or equals to it means that x0 ranges from x0 minus a to x0 plus a. And don't forget that y minus y0 less than or equals to b, it actually implies that y0 minus b, that y0 ranges between y0 minus b and y0 plus b. So the last thing we are going to consider now is the uniqueness of solution. Do you know that in this class, each and every one of us, we are unique? In this course, there is nobody that is bearing my name, that is from my same town, that have everything with me. So even if I thought there exists another person like that, then it means that that person and I, we are equal. That is what uniqueness is all about. But how do we know that a particular solution is unique? It's very important. The number one thing is that, in this case, we are talking about y is changing with respect to what? With respect to x. So in that case, if y is changing with respect to x, then out of dependent variable and independent variable, which one is most important? I think the main important thing is the dependent variable. So the dependent variable will let us know. It tells us a lot of things about the uniqueness of the problem. Because in that case, we need to consider partial derivative of f with respect to y. If we can obtain that, then that will help us to know about the uniqueness of the solution. Don't forget that I've said that the function fx, y, it helps us a lot to know the existence of the solution. Function fx, y, it helps us to know a lot of things about the existence of the solution. But when we're not talking about the uniqueness, we need to really focus on how the function is changing with respect to the dependent variable. That is what we need now to know the uniqueness now. So in that case, we can say that if partial derivative of f with respect to y is continuous for all x and y in R, please don't forget x and y in R is too broad. We need the condition x0, y0 to be able to come up with a perfect domain. Okay, now, so that is the first thing. The second thing now is that the partial derivative and then the absolute value, it must be less than or equals to m for all x and y in the domain. So if that is the case, then we can say now that the solution we are talking about is actually exists and the solution is actually unique. Thank you very much. So let me quickly introduce you now. Look at this first problem I've explained to you now. Now you notice that in this case, we can quickly make use of this to have this to my x-axis. This is my y-axis. Then let me locate the point 2, 3. The point 2, 3, that means that this is 1, this is 2. Then what about y? Y is 3. This is 1, this is 2, then this is 3, then this is my 3. So where is the point now? This is the point. So what do I need now? It means that I need a particular triangle in such a way that this is at the center. And how do I go about it? All I can say is that I can say that x minus 2 less than equals to a, then y minus 3 less than equals to what? Less than equals to b. So that is what I need to form the triangle. But without wasting our time, let's proceed and solve this problem. How do we solve it? We can see now that my dy is equals to 2x plus 1 multiplied by what? Dx. Then the next thing is for me to integrate both sides. If I integrate the y, I will have y. If I integrate this one, I will have 2x, then 2 over 2. Then if I integrate one, I will have what? I will have x, then I will have my constant of integration. So how do I find c now? I'm going to find c using the point x naught equals to 2, then y naught is equals to what? 3. So that means that this my y is now equals to 3. Then these two will cancel 2. Then I'll have 2 squared plus 2 plus c. And no, 2 squared is what? Is 4. 4 plus 2. That's 6. Then 6 will come to this side, then our minus 3 is equals to c. Then in that case, my solution y of x is equals to x squared plus x minus c. So looking at this problem now, this is the function I was talking about. You will now see that, minus 3. You will now see that this function I'm talking about, this function is what? Is continuous. This function is what? Is bounded.